Picture the sun as a giant campfire in the sky, burning, roaring, spitting heat into space. That image feels obvious, and it's also wildly misleading. Because the sun isn't on fire the way fire works on Earth. It doesn't have a solid surface, and the hottest part isn't even the bright yellow part you see. So what are we actually looking at when we look at the sun? The sun is the most familiar object in our sky, yet we describe it with the wrong mental model: a glowing, burning ball with a crisp edge. In reality, nearly every part of that sentence is off. The sun is plasma, not flame. Its surface is more like a depth where light finally escapes. And the visible layer, what your eyes call the sun, isn't where most of the action happens. This matters because our lives run on solar behavior. Power grids, satellites, GPS, radio, aviation, even the internet's undersea cables can all feel the sun's mood swings. The twist is that those mood swings come from magnetic forces, not combustion. And once you see the sun as a magnetic machine, the weirdest solar facts suddenly make sense. Start with the most common mistake. The sun is on fire. Fire is chemistry. It's molecules grabbing oxygen, releasing energy, making hot gases and light. But deep in the sun, there's no oxygen to burn. And even if there were, atoms don't really behave like campfire fuel. They're torn apart. At the sun's core, the temperature is around 15 million degrees Celsius. The pressure is so brutal that hydrogen nuclei smash together and fuse. That fusion turns a tiny bit of mass into energy. Not metaphorically, literally. E equals mc squared is happening, non-stop, in a region only about the inner quarter of the sun's radius. And here's the part people miss. The light you see today didn't shoot straight out from the core. Photons can take thousands to hundreds of thousands of years to fight their way outward, getting absorbed and re-emitted like someone trying to leave a stadium through a crowd. The sunlight hitting your face might be older than the Roman Empire. So if the sun isn't fire, what is it? A fusion-powered plasma sphere. And the real story starts at the edge where that trapped energy finally escapes. When you look at the sun, it seems to have a sharp outline, like a solid disk. That edge is an illusion created by transparency. The sun doesn't have a solid surface you could stand on. What it has is a zone where the plasma becomes thin enough that light can finally travel freely. That layer is called the photosphere, and it's only a few hundred kilometers thick, basically nothing compared to the sun's size. This is also where the yellow sun myth sneaks in. The sun's light is actually close to white. It only looks yellow from Earth because our atmosphere scatters blue light. In space, astronauts see it much whiter. Zoom in on the photosphere and it's not smooth at all. It's granular, like boiling oatmeal. Those bright cells are convection, hot plasma rising, cooling, and sinking back down. Each granule can be about the size of Texas, constantly forming and collapsing. But here's where it gets weird. Above this relatively cool photosphere, about 5,500 degrees Celsius, the temperature shoots up. The sun's outer atmosphere, the corona, reaches 1 to 3 million degrees. So the hottest layer is farther from the core. That shouldn't happen, unless something other than simple heat flow is in control. The key to the sun is magnetism. The sun rotates, but not like a rigid ball. The equator spins faster than the poles. Inside, plasma flows and churns. This motion acts like a dynamo, generating magnetic fields that twist, stretch, and braid like rubber bands under tension. Sunspots are where those magnetic fields punch through the photosphere. They look dark not because they're cold like ice, but because they're cooler than the surrounding surface, still thousands of degrees, while intense magnetism suppresses convection. And when magnetic fields tangle too far, they can snap and reconnect. That reconnection releases enormous energy, launching solar flares and coronal mass ejections, billions of tons of charged particles hurled into space. The sun can explode without losing anything solid, because it's not throwing chunks of itself. It's throwing magnetized plasma. This is why the corona can be so hot. Magnetic waves and reconnection can dump energy into the outer atmosphere, heating it from above like an invisible blowtorch. And it's why space weather is real weather. If one of those eruptions aims at Earth, it can induce currents in power lines, degrade satellites, and light up the sky with auroras that creep toward the equator. So the sun isn't a steady lamp. It's a dynamic magnetic system with a pulse. We've been looking at the sun like it's a simple object, a burning sphere with a surface. But the better model is this. The sun is a layered, flowing plasma machine where light struggles outward, where the surface is just the depth where photons finally escape, and where magnetism runs the show. That's why the sun's edge is a transparency effect. That's why the visible layer isn't the hottest. That's why sunspots, flares, and monster eruptions happen at all. The sun isn't behaving like fire. It's behaving like a star-scale electromagnetic generator. And here's the lingering mystery. We still can't perfectly predict when the sun will unleash its biggest storms. We can watch magnetic fields twist. We can see active regions form. But the exact moment they snap? That's still partly a guess. Which means the most familiar thing in our sky is also one of the most deceptively complex machines we've ever studied. The sun isn't a campfire. It's a magnetic ocean, glowing because energy fought for centuries to escape. And the next time you see that simple yellow disk, remember, you're looking at a moving boundary, not a surface.